This video is a summary of all the information you need to know about acids and bases for National 5. It goes through things in a small amount of detail, just what you need to know. If you're feeling like you want to go into more detail, there are individual videos on each individual topic within this same playlist. So when it comes to acidity, we measure acidity on the pH scale. We can use a chemical called universal indicator, which changes colour to reveal the pH of a substance, or we can use a pH meter, which gives us a numerical value for the pH of a solution. We can judge whether something is an acid, neutral, or an alkaline, which is another word for a base, based on either the colour or the numerical value we get from pH meter. Acids have a pH under 7, so even 6.9 would be an acid, and they turn universal indicator red, orange, or yellow. The stronger the acid is, the more towards the red side it is. Alkalis will have a pH more than 7, and they will usually turn universal indicator blue or purple. Purple is the stronger alkali than blue. And if we have a substance right in the middle that has a pH of exactly 7, it is neutral and it would turn universal indicator green. Now we need to know when certain elements form oxides, those oxides can be acids or they can be alkalis. There are 3 nonmetals, carbon, nitrogen, and sulfur, that when they burn in oxygen to produce oxides, their oxides are acidic. So carbon dioxide, nitrogen dioxide and nitrogen monoxide, and sulfur dioxide, you need to know that those all make acids. They are all gases, and when they dissolve in water in the air, they can produce acids. Now, how we get non-metal oxides? Well, there are man-made sources. Burning fossil fuels is a big one, car exhausts, and also in chemical manufacturing. However, there are natural sources of carbon dioxide and sulfur dioxide. Respiration, a process which keeps every living thing alive, releases carbon dioxide into the air, including ourselves. And volcanoes release a very high percentage of the total sulfur dioxide that makes it into the air. Now, acid rain itself can lead to destruction of buildings. It can make soil more acidic, which can lead to algal blooms, which you'll know about if you study biology, or it can damage the habitats of animals by making the soil too acidic. If acid makes its way into water, like rivers, lakes, and oceans, it can lead to a loss of biodiversity by causing coral reefs to bleach, meaning turning white, which is killing the coral, and ultimately the death of animals that rely on things like coral. The ways to prevent acid rain would be to move towards greener energy that does not rely on fossil fuels, to prevent nitrogen oxide and dioxide being released from cars. We can have catalytic converters, which are now standard on cars, using public transport to avoid mass use of cars, and also having stricter regulations on the emissions that factories and countries can actually contribute towards the atmosphere. Now, those were our non-metal oxides: carbon dioxide, nitrogen dioxide and monoxide, and sulfur dioxide. Those are all acids. All metal oxides are bases, but it's only when a base dissolves in water that it is an alkali and can affect the pH of water. So if a metal oxide dissolves in water, you will get an alkali solution and it will change universal indicator blue or purple. So it'll have a pH greater than 7. If a metal oxide cannot dissolve in water, if it is insoluble, it cannot change the pH. And therefore, if you have universal indicator in a solution like that, it will stay green. And you can use the table at the bottom of page 10 in your DUTA booklet to work out whether or not a metal oxide is soluble or not. The key is if there's a letter I, it's insoluble. If there's a letter V or VS in the box, then it is soluble. Now, water as a molecule has the formula H2O. Water can split into ions. When water splits into ions, we get the hydrogen ion, H+, and we get the hydroxide ion, OH-. It is the hydrogen ion that makes things acidic, and it is the hydroxide ion that makes things basic or alkaline. You need to know the formula and the names of each of these ions and what they are responsible for. Now, when we say that the hydrogen ion makes things acidic and that the hydroxide ion makes things alkaline, it doesn't mean that if you are an acid, you only contain hydrogen ions. It is a balancing act between the two. If you are an acid, you have more hydrogen ions than hydroxide ions. If you are neutral, that's when everything is balanced. You have the same concentration of hydrogen ions as hydroxide ions. And if you are an alkali, that means you have a higher concentration of hydroxide ions than hydrogen ions. Again, you need to know the relative number of hydrogen ions compared to hydroxide ions for an acid, neutral, an alkaline or basic substance. Now, pH measures the concentration of hydrogen ions in water. The higher the concentration of hydrogen ions, the lower the pH. If we dilute an acid, meaning adding water to it, what that does is it lowers the concentration. If we lower the concentration of hydrogen ions, it means the pH will actually go up. And so we can plot a graph of that. Now, you can be asked in an exam to plot a graph like this. It usually has one plot drawn and you have to draw the rest of the graph. The graph usually does not have a complete scale. So you need to at least make sure that on the scale, you put in a number 7 where your graph is going flat. Because if you add in water, you will get closer and closer to the pH of water, which is 7, but you cannot go above 7 by diluting. If it is an alkali, the graph will look just the same but reflected. It'll get close to 7, but it will start off higher. Now, when we react an acid with a base or an alkali, what we're doing is we are reacting the hydrogen ions and the hydroxide ions with one another. And when they recombine, we form water. So anytime we do a neutralization reaction, we get water. Our hydrogen ions were attached to something else, and our hydroxide ions were attached to something else. Those other things, when the neutralization reaction happens, they will come together to form something called a salt. And we need to be able to name those. We also need to know these 3 equations for neutralization. So you need to know that if a chemical is a carbonate, hydroxide, or oxide, then it is a base. If it is a metal oxide, a metal hydroxide, or a metal carbonate, it is a base. And acids react with these 3 things. When an acid reacts with a metal oxide, you get a salt and you get water. When an acid reacts with a metal hydroxide, you get salt and water as well. When an acid reacts with a metal carbonate, you get salt, you get water, but because you have that carbonate, you also produce carbon dioxide gas. Now, in an exam, you cannot write the word salt. You will have to write a specific name, and we will get onto that later in the video. Now, carbon dioxide is a gas that you need to know how to prove that it has been produced. This is the answer. Carbon dioxide will turn lime water cloudy. Lime water is the chemical you use. It turning cloudy is what you see if carbon dioxide is added to it. You need to say all of that to get a mark. Why it's going cloudy is because you are forming something called calcium carbonate, which is a precipitate, and you're forming a solid by reacting the carbon dioxide with that lime water. There are 3 common acids and then another one that you might get asked about, which is related to Unit 2. You will need to know the formulas of these acids. You will need to know what sort of salt comes from which acid. You also need to know for sulfuric acid, it will react faster and make more gas because it has a higher concentration of hydrogen ions. And you must call them ions, okay? Because it is H2SO4 and all the other ones only contain 1 hydrogen. When sulfuric acid reacts, it will always produce more gas and it will react faster because it has a higher concentration of H+ ions. Or you can say hydrogen ions as long as you say hydrogens. So you need to know the names of the acids and you need to know their formula and the salt that is produced. Hydrochloric acid, HCl, it will make metal chloride. Nitric acid, HNO3, it will make metal nitrates. Sulfuric acid, H2SO4, it will make metal sulfates. Ethanoic acid, which is the acid in vinegar, it will make metal ethanoates. You do need to know the formula of ethanoic acid because it's part of Unit 2. When it comes to naming salts, if you use hydrochloric acid, you will form a chloride. Now, the name of a salt always has 2 parts. You have the metal part, which comes from whatever metal oxide, hydroxide, or carbonate you used, and you have a second part, which always comes from the acid. Hydrochloric acid always makes a metal chloride. So example here is if we reacted hydrochloric acid with potassium carbonate, the salt would be potassium, and chloric acid, hydrochloric acid, gives chloride as the name, so potassium chloride. Nitric acid, HNO3, forms nitrates. So again, the metal part of the name comes from whatever metal oxide, hydroxide, or carbonate, whatever base you're using, and because it's nitric acid, it's going to end in nitrate. So if we reacted nitric acid with copper oxide, we would get copper nitrate. Sulfuric acid, which is H2SO4, it forms sulfates. So again, the metal part of the name comes from whatever metal base, oxide, hydroxide, or carbonate you've used. So if we reacted sulfuric acid with calcium hydroxide, we would produce calcium sulfate. With ethanoic acid, exact same thing, except the salts are going to end with ethanoate. So if we used ethanoic acid with sodium hydroxide, we would get sodium ethanoate. Now, metals can also react with acids. Acids can also react with metals. Metals do not produce water. It is not a neutralization reaction. We name the salt in the exact same way. The salt has 2 parts. It will be a metal something, The metal comes from whatever metal you used. The second part of the name comes from whatever acid you used. So if zinc metal is reacting with sulfuric acid, your salt is going to be zinc sulfate. We also have what is the test for hydrogen gas, because hydrogen gas bubbles are being given off. You need to know that hydrogen gas burns with a pop. Now, on the back of your data booklet, the last page, there is a list of metals. And on that list of metals, there is the word hydrogen. Now, you can work out whether or not a metal will react with an acid based on where it is on the data booklet. If the name of the metal is above hydrogen, it will react with an acid. If it is below the word hydrogen, it will not react. Okay, and we can see this box here indicating that. Now the final, an experiment you need to know with acids and alkalis is called a titration. Now titration is used to work out the concentration of an alkali that we do not know the concentration of using an acid that we do know the concentration of. We use a device called a burette to deliver the acid downwards through a tap, and we use a pipette to fill the alkali into the bottom. So when we're looking at a burette, it starts at the number 0 at the top and it goes downwards. When liquid is in it, the liquid curves and causes something called the meniscus to form. Whenever we are reading a burette, we read from the bottom of the meniscus. And you want to be looking at it. When it comes to a titration experiment, you must always rinse your burette out with whatever acid is going in. Okay, that is the last thing you must rinse it with. You can rinse it with water first, but you must rinse it with your acid. Here, you can use a measuring cylinder. It is better to use a pipette to add in your hydroxide into your conical flask. Into the bottom, you need an indicator. This indicator is not universal indicator. The indicator will change depending on what acid and what alkali you're using, so do not give it a specific name. In a titration, you add an indicator to your alkali, and you will keep adding acid until it changes color. When it's changed color, you read off from the burette how much acid you added. And then importantly with the titration, you must repeat it until you get results that are concordant. Results are concordant if they are the same or within 0.2 centimeters cubed or milliliters of one another. In this table, you can see that 4 titrations were done. Only these 3 are concordant with one another. So if we're asked to work out an average, our average is only going to be an average of our concordant results. Ignore the first titration as it is always a rough one. So our average is going to be 15 plus 15 plus 15.1, which is 45.1, and we will divide that by 3, which gives us 15.33 as our average. They like to put in a question getting you to work out the average, and they will always put in one result that is not concordant. You can only take an average of concordant results. We've got 2 things to get through, insoluble products and spectator anions. Now, a precipitation reaction is one where a solid is produced from 2 liquids or a liquid and a gas. The solid that forms is called your precipitate, and you can predict if a product will be a solid by finding out if it is insoluble from page 10 of the data book. You can also sometimes just know by looking at things called state symbols. So S is for solids, AQ stands for aqueous, which means it's dissolved in water, L for a liquid, and G for a gas. Now in this reaction, we start with a solid and we're ending up with aqueous, liquid, and gas. This one would not be a precipitation reaction. Precipitation is when we have liquids, aqueous, and gases to start with, and we finish with something that is solid. So in these reactions, the top one, aqueous, aqueous to solid, will be a precipitate, but the bottom one, aqueous, aqueous to aqueous, would not be a precipitation reaction. In a reaction that is not a precipitation reaction, we will end up with ions in our starting material and ions in our product. Now every acid, when it dissolves, will give us H+ ions and then whatever is left over. Every hydroxide, when we dissolve, will give us hydroxides and what's left over. Every salt, we just split the salt in half and it will give us whatever ions would form from those two parts. Now, spectator ions are what we call it when ions are in the solution that we start with and also in the solution that we end up with. In other words, they have not done any reacting, they've just watched the reaction happen, which is why they get called spectator ions. They always are aqueous. So we cannot get spectator ions from a precipitation reaction. So if we look at an example of a reaction, we've got our sodium hydroxide, which is Na+ and OH-. We've got our hydrochloric acid, which is H+ and HCl. We've got our sodium chloride, which is Na+, Cl, and we've got our water. What we want to do is look for what ions do we have that are the same at the start and at the end. We have got not hydrogen, not hydroxide, because they end up here. What we have are our sodium ions and our chloride ions. We have them at the start, we have them at the end. Those are our spectator ions. We can only get spectator ions if our salt is AQ, and our spectator ions will always be the ions in the salt. So that has been a quick review of everything you need to know about acids and alkalis. Again, if you want to go into any of the topics in more detail, there are more detailed videos on each individual section.